The subject for ultrasound physics is quite broad. Only a few items can be covered in this. The first part will cover the physics and physical principles of the B-mode ultrasound. The second part will address hemodynamic studies and flow visualization. Ultrasound image is constructed by emitting a sound with frequency higher than 20 kHz and receiving the echoes from different tissue structures called reflectors. By measuring time between emission of the signal and receiving of the echo, an ultrasound system is placing pixels of different brightness at different depths, creating an image of the tissue. This is a brightness mode or B mode of ultrasound imaging. The ultrasound is a mechanical wave consisting of high and low pressure areas propagating through the tissues with certain velocity. The amplitude of this wave reflects the highest pressure point, and the period is the time between emission of highest pressure. The frequency of the ultrasound is the number of periods per second, and it is controlled by ultrasound system. The wavelength, on the other hand, depends on the speed of ultrasound, which depends on acoustic impedance and is different in different tissue. A speed of ultrasound in the soft tissue is on average 1540 meters per second, and it is used as a reference value in ultrasound equipment. Please notice that the speed of ultrasound in the blood is 30 meters per second higher than the soft tissue. Such difference may cause small but sometimes significant error in measurements. In this example, the ultrasound wave traveled through the 10 centimeters of the soft tissue and then through a vein in diameter 1 centimeters. The reflection from the closest vein wall to the transducer will arrive at about 65 microseconds after transmission. It will take additional 6 microseconds for ultrasound to reach the opposite wall of the vein and an equal time for the echo to travel back to the interface with the soft tissue. The total time for receiving the reflected wave from the second wall of the vein is slightly more than 142 microseconds. Currently used ultrasound systems assume that the propagation velocity of the ultrasound waves is constant 1540 centimeters per second. Thus, an ultrasound system will underestimate the vein diameter. This measurement error is relatively small, just 2%. However, it may become clinically relevant, for example, when looking at the aortic aneurysm growth over time. Diagnostic ultrasound systems used pulsed wave emitting short pulses of the ultrasound at certain frequency, called pulse repetition frequency. Therefore, there are two sets of physical parameters of the ultrasound. One relates to ultrasound wave itself, its frequency and wavelengths, and the second relates to the pulsed ultrasound with the pulse repetition frequency, or PRF, and the spatial pulse length. The spatial pulse lengths determine the axial resolution, the ability of the ultrasound to image separately two closely positioned reflectors. If two reflectors are positioned at a distance less than a half of the spatial pulse length, the echo from the second reflector will overlap the echo from the first, making two objects appear as one on the ultrasound image. The wavelength of the ultrasound determines the absolute limit of resolution that cannot be improved by PRR. Lateral resolution is an ability to differentiate between two reflectors positioned side by side. This resolution is mainly determined by ultrasound transducer and the settings of the system. This resolution is the best in the narrowest area of the ultrasound beam, called focus. The axial resolution is always better than lateral resolution. The combination of the two gives us the volume resolution, which in typical settings of vascular ultrasound is about 4 microns. Such volume resolution makes it possible to image red blood cells or even their elastic conglomerates. This is one of the reasons that blood appears echolucent on the ultrasound image. As ultrasound travels through the tissue, it loses its energy due to absorption, reflection, and refraction. This attenuation depends on the properties of the tissues and on the frequency of the ultrasound. The trade-off is the resolution, which is higher with a higher frequency ultrasound, while penetration is worse. The boundaries between two different media with different acoustic impedance acts as a mirror causing specular reflection. The greater is the difference in acoustic impedance between the two media, the greater reflection and the smaller is transmission. When the sound wave length is greater than the size of a structure it comes in contact with, it creates a uniform amplitude in all directions, Rayleigh reflection. Specular reflection is the basis for creating an ultrasound image. Because the red blood cells is about 100 times smaller than the ultrasound wavelengths, apparent Rayleigh reflection may create an impression of visible blood. As ultrasound beam continues traveling through the boundaries between the two different media, it changes its course. The change in the angle is proportional to the speed of ultrasound in this medium. Vascular ultrasound, by convention, uses an inclination angle of 60 degrees to the vessel wall. The 20 meters per second difference in the speed of ultrasound makes the beam to deviate to about 2 degrees from the original direction. Ultrasound systems assume that the direction of the beam remains constant. In this example, refraction causes a 1 millimeter shift in the position of the posterior wall of carotid artery of the ultrasound image, creating an impression of 50% stenosis. Accounting for this error results in a significant correction of the degree of stenosis. A combination of reflection and refraction can explain some of the ultrasound artifacts. The closest wall of the blood vessel acts as a curved mirror, resulting in a weaker echo received by the transmitter. The refraction results in a conversion of the beam and more echoes towards the transducer. The result is the posterior wall of the vessel looks brighter than the wall that is closer to the transducer, the phenomenon called acoustic enhancement. In part 2, we'll talk about Doppler ultrasound and the blood flow imaging. The blood flow velocity measurement and most of the blood flow visualization modalities are based on the Doppler effect. When a reflector like red blood cells in the blood is moving towards the transducer, it increases the frequency of the echo compared to emitted ultrasound. When the flow is moving away from the transducer, the frequency of echo decreases. This shift in frequency is directly proportional to the flow velocity, allowing to measure it. Most of the peripheral vasculature can be unsonated only at a certain angle. By convention, vascular studies are done at the insonation angle not exceeding 60 degrees. This angle is taken into account by using Doppler equation. A spectral Doppler measurement of the Doppler shift in this area called sample volume. Then it continuously displays all velocities in this volume as pixel line at every time point. The brightness of every pixel corresponds to a relative prevalence of a specific velocity. The spectrum width corresponds to the entire range of detected velocity within a sample volume at a time point. In normal arteries, the spectrum is relatively narrow. When taken in the center of the artery during a systole, this spectrum does not include low velocities, leaving a visual gap between the velocity trace and the baseline called spectral window. The velocities in the turbulent flow, such as in the area of stenosis, are ranging from high to zero, sometimes to negative velocities in the reverse flow component. This spectral window is no longer present. This phenomenon is called spectrum broadening. The flow velocity profile in blood vessel is such that highest velocities are in the center of the vessel and lowest velocities are close to the vessel wall. A small sample volume positioned in the center of the vessel lumen has the most narrow spectrum. Increases sample volume leads to broadening of the spectrum even in the normal vessels. The three-dimensional pattern of the blood flow is much more complex, especially in the areas of bifurcation, curvatures, and orifice of the larger branch. Correct position of the sample volume in such areas of blood vessel is very important. When the sample volume is placed in the area of flow separation, in a normal vessel, it may give a false impression of turbulent flow. Arterial walls also move during the flow cycle, creating a Doppler shift similar to the blood flow. This can be a source of error. To minimize such error, the ultrasound systems employ the wall filter. In the Doppler modalities, an ultrasound system registers the frequency shift and the intensity of the echo signal. The low intensity noise is rejected. Then the area of low Doppler shift is also eliminated by the filter. The size of the wall filter, depicted by the green box on the velocity scale, corresponds to rejected velocities. Although this filter eliminates mostly the noise from the wall movement, sometimes it can affect the interpretation of the Doppler waveforms as being monophasic rather than multiphasic. Ultrasound systems measure the frequency shift and then calculate velocity using Doppler equation. The angle of the angle correction cursor is used for this calculation. This angle can be changed by a sonographer either during the test or after the test is complete. These images demonstrate that a change in position of the angle correction cursor from 60 degrees to 30 degrees results in a significant decrease in measured velocity in exactly same image. In pulse Doppler mode, the ultrasound is emitted in short pulses at a certain frequency. So the measurements of the Doppler shifts are also performed not continuously, but at the pulse repetition frequency. Let's say this curve displays the echo signal from an artery. It is higher than the pulse repetition frequency of the ultrasound. So the measurements done at a lower frequency, and as a result, the curve results from these measurements has significantly different frequency, leading to incorrect value of the calculated velocity. This phenomenon called aliasing. Another demonstration of aliasing is when you following a point marked here by a star on a clockwise spinning wheel at a certain time intervals. If sampling frequency is sufficiently high, you can see that the wheel is turning in the right direction. However, if your sampling frequency is low, you are getting the impression that the wheel is spinning in the opposite direction. Maximum Doppler shift frequency that can correctly measure with the resulting no alliances is called Nyquist limit. A Nyquist limit is equal to half of the pulse repetition frequency. When the Doppler frequency shift exceeds half of PRF, aliasing occur like on the image in the left. A true aliasing in the spectrum Doppler image can be corrected only by increasing the pulse repetition frequency. The apparent aliasing depicted in image B is not really aliasing, but is caused by inadequate scaling. This artifact can be corrected by either moving the baseline of the velocity scale up or by increasing the scale, which is the same as increasing pulse repetition frequency. Creation of a real-time color image using Doppler shift analysis requires a computer power that far exceeds existing ultrasound systems. Instead, color images are constructed not by measuring the Doppler shift, but using autocorrection technique. Consecutive sound pulses are transmitted into the same sample volume. The second echo comes back at a different phase of the signal. This phase difference is measured and the mean Doppler shift is calculated. The difference is obtained from 8 to 16 samples per each line of the ultrasound beam. Then the data undergoes spatial and temporal averaging, and a two-dimensional color map is displayed. The color represents the direction of the flow and the magnitude of the velocity, but the information is qualitative, not quantitative. The color bar should not be used to estimate the flow velocity. Even more, the scale is also not linear. Color map provides information on where velocities are higher or lower, but not on the magnitude of the difference. Similar to spectral Doppler, the flow intensity is eliminated in the color Doppler. Echoes with intensity higher than those from the blood are rejected, setting the color preference. In order to eliminate the flash artifact caused by movement of the vessel wall, the average of the Doppler shift of the entire color is artificially increased. The wall filter, depicted as a box on the color scale, uses a different technological solution than the spectral Doppler. This solution makes color Doppler less sensitive to low velocity and poor resolution near the vessel wall. The color Doppler uses the same Doppler equation to assign different colors to different directions of the flow. When the blood flows towards the ultrasound beam, in other words, at an acute angle to the beam, it depicts as a positive part of the color scale. When the blood moves away from the transducer, it depicts a negative part of the scale. If the flow is at an angle to the ultrasound beam, the Doppler shift is zero and no color is assigned. This limits the ability of the color Doppler to image turning points of the vessel. The end of the color bar in the color Doppler image represents the Nyquist frequency. A color scheme may be presented as a circle rather than a bar. When the flow velocity exceeds the Nyquist limit, aliasing occurs, and the color assigned to the parts of the scale that are depicted as the opposite direction of the flow. Clinical interpretation of still color Doppler images is sometimes challenging. The appearance depends on the point when the image was frozen. It is always preferable to have a combination of color and spectrodoppler modalities rather than a color flow image alone. Power Doppler uses a very different approach to flow visualization. It eliminates the areas with Doppler shift below the set threshold and displays color that reflect not the Doppler shift, but the intensity of the echo. This difference in modalities provide complementary information. The color Doppler shows the direction of the flow and qualitative assessment of its velocity. The power Doppler visualizes areas of the flow that are not displayed by color Doppler, the near wall flow and the turning point of the vessel. In summary, we cover the main parameters of the ultrasound waves, axial and lateral resolution of ultrasound, attenuation, reflection, and refraction, and some principle of Doppler ultrasound and blood flow imaging.